So this is our last lecture. I'm going to just jump into the last topic, which really requires several more lectures, and we'll just see how far we get. So if you look in any physics book or physics journal with an something that is using non-equilibrium Green functions, it won't look anything like the way we've described it so far. It'll all be formulated in terms of second quantized operators, which is what we're going to start talking about now. This is sort of the second part of the course, sort of reformulating everything in terms of second quantized operators. Okay, so what the heck is this? These are your creation and annihilation operators that you've probably run into somewhere before. And these are the kind of operators that you use to describe a harmonic oscillator, but formally they look the same, but they're different. And it's a compact representation of a Slater determinant. It's called the we're going to be working on what's called the occupation number representation. And it tells you about how many electrons are in which orbitals. So if we have n electrons in n orbitals, 1 through n. So the way you represent a state in this representation is we have n orbitals, you have a ket, and the information in the ket, they're ordered according, you order the orbitals 1 through n. And what's in the ket tells you how many electrons are in each orbital, where in n sub I, for electrons, is either going to be 1 or 0, since you can only have 1 electron in an orbital, because they're fermions. But this can be, so this is for fermions. And for bosons, then Ni could be any integer, because you can, there's no limit, so 0, 1, infinity. For bosons. It's the same sort of representation, but it's just, for fermions, it's either 0 or 1. For bosons, like phonons or photons, it could be any integer, positive integer, or 0. The vacuum state would just be all zeros, everything empty. And for shorthand, so we don't have to keep writing this over and over again, I will, in shorthand notation, just refer to that as like that. This general state, this guy here, is created by applying creation operators to the vacuum. So our general state n1, n2 through nn is equal to a1 dagger raised to the n1, and so n1 a2 dagger, n2 dot 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 a n dagger raised to the n sub n. So these, I'm raising them either to the or other way around, either to the 0 power or to the first power for fermions. Acting on, so these are all acting on the vacuum state. Right, so you create your general state by acting on the vacuum state with a bunch of creation operators. And so, you know, if I just, in general, in a single electron picture where you would have, say, 1 electron in the band, if you have AI dagger acting on the vacuum, it would generate, 1 electron in orbital, whatever you want to call this, phi sub I, in this shorthand notation, which now means not just the state phi sub I, but 1 electron in state phi sub I. So these creation for our fermions, which is all the time we have to be focusing on in this one lecture, for fermions, and we're going to be just only considering an orthonormal basis. So last time we talked about a non-orthonormal basis, and now we're just back to an orthonormal basis. So for an orthonormal basis, you have the anti-commutation relations for your fermions at AI, AJ dagger. So the anti-commutator just means AI, AJ dagger plus the dagger of that, a Hermitian conjugate, is equal to delta ij. And your standard anti-commutation relationship. And if that's anything else gives you 0. So AI comma AJ is equal to AI dagger, AJ dagger is equal to 0. But if you look at these relationships here, what this means is if you switch the order in which you create two particles, you introduce a sign of -1. And that's sort of like switching the rows or columns in a Slater determinant, right? In a determinant, if you interchange two rows or two columns, you change the sign of the determinant. So switching two of these is like changing rows or columns in a Slater determinant. You pick up the sign of -1. So these you can think of these now as, you know, these orbitals, right? So these are just the occupation, and they're ordered according to some basis set, which are my orbitals, you know, phi 1, phi 2, phi n, some single particle orbitals, just like you would create a Slater determinant. And you can think of the orbitals as the orbitals that we've been dealing with for the past 2 quarters, your local atomic orbitals, for example. Okay, your normal basis, tight binding basis that we've been working with for a while now. A basis, we've never done much with the position basis, since numerically it's not particularly useful, but often, like in Feder and Waleka, you'll see the theory develop using field operators. And these are just creation and annihilation operators in the position representation. Psi dagger of R, where now these are not wave functions. These are creation and annihilation operators. I'll put a hat over them. They're operators. So when they act on the vacuum, they create a particle of position R. So, and using this shorthand notation, psi dagger of R acting on the vacuum state creates a single particle at position R, 1 electron in state R. So the relationship between these field operators, which are just creation and annihilation operators in the position representation, and the ones in the localized orbital representation, or AI, we just find in the same way. It's just a change of basis, right? So if we look at R, that's equal to some I put in a complete set of states, alpha I, R. And this is just phi I star of R, right? Or alpha, okay, bad notation, but I'll call this phi I star of R. That's just my localized orbital. My localized orbital. And this is just AI dagger acting on the vacuum state. Right? Because now we mean not just the wave function itself, but an electron in that orbital. Right? This is what we said. Here it is. Here. I call it a phi I. I'm calling it alpha I. I'm sorry, I'm mixing phi's and alphas. Okay? And so just putting that together, we have so that R, which is, psi R dagger acting on the vacuum, is some I phi I star of R AI dagger acting on the vacuum, which means that all this stuff is psi dagger of R taking the Hermitian conjugate, then psi of r is just related to AI, which is some I phi I of r AI. I've got the relationship between what they call the field operators, which are just creation and annihilation operators in position, and our creation and annihilation operators in localized orbital representation. Does it bother you when I take the Hermitian conjugate of this first expression, this guy here? If I take the Hermitian conjugate of this expression to get this expression, that I don't reverse the order of the phi and the AI? Is that a problem? Why?
Phi's number is over.
That's right. So in this in like, this is second quantized. So in our earlier representation, phi was a state, and the operators acted on phi. Now the operators are the AI and AI dagger, and phi is just acting as a weight, sort of an amplitude to the operators. But these are the operators. These are the only things that are operating in this representation, the AI and the AI dagger. And I guess I should put hats here. These are my operators, right? I mean, if you didn't know better and you just looked at this expression down here at the bottom, it looks just like the expression for your wave function psi, expanded in terms of the localized orbital basis phi, and the amplitudes would be AI, right? But now it's kind of the opposite. This is the amplitudes are the phi, and the operators are the AI, and psi as an operator is no longer a wave function. Okay, so it can be a little sort of topsy-turvy when you first see this. But it's because we're in this occupation representation where these operators are creating and annihilating particles in specific states. Okay, so we have our field operators. Given the field operator, psi, we can immediately write down the electron density operator. So n of r, the operator, is just psi dagger psi of r. So if you let this operator operate on any random state, and so if you think of psi dagger psi of r operating on some state where you order, r is continuum, but let's think of it as I can order all my positions, r1, r2, dot dot dot, r dot 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 dot, r blah blah blah, and right, there's an infinite number of r's. But the one that this is acting on, here's my r. So here's r, r, and r. So these psi daggers are acting on that position r, right? And so if psi of r hits, when psi of r hits this and there's no particle there, I just get 0. The whole thing is 0, and I get a 0. If there is a particle there, it removes the particle, and then psi dagger puts it back. And so this is sort of a test on whether there's a particle there or not. I'm going to get the ket back, or I'm just going to get 0. And so when I take the sort of thermal ensemble average of this, so n of r, and this is no longer an operator, which is the thermal and a sort of statistical thermodynamic average of this, I just get my electron density at position r. It would be like a thermal statistical average using, say, a grand canonical ensemble or something. And then if we expand this back out in terms of going from this position basis back to our localized orbital basis, we have that n of r is equal to sum ij, ai dagger, aj, phi I star of r, phi j of r. Just doing that basis transformation from the psi's to the the localized orbital basis, right? Using this relationship here, just plugging in these expressions for my size, right? So I plug in these two expressions for my psi dagger and psi. I get that. So the brackets just go around, the average just go around the operators, yeah.
The red line, the left side is operator, the right side is the value, mean value.
Say that again.
For the red line, the left NR is on operator, right?
Well, N hat is the operator. This is just your usual electron density on the far left. This is just your density. Here's the average of the operator, which gives me my density. And so looking down at the next line, in the last lecture we actually showed this expression when we were talking about calculating electron density. This is just your density matrix, which is equal to integral dE over 2 pi Gn Ji of E. If you go back and look at the last lecture, I think we got that far. And it's now, well, it will be in the updated notes. When we talked about calculating electron density and with DFT codes and such, we had this same expression where we had this density matrix with its integral of Gn in there. And just by equating the two expressions, we'll see that what I've put in the underscore has to be true, and later we'll show that this is indeed exactly the definition of our G sub n in the localized orbital representation. All right. What else can we say? Okay, so now if we take this expression and we integrate, our electron density over all position, we just get the total number of electrons. So the total number of electrons n is integral over all position d cubed r n of r, which is equal to sum ij, ai dagger aj, integral d cubed r of phi I star phi j of r. And since this is an orthonormal basis, this just gives me my Kronecker delta function, which collapses one of the sums. So I have that n is equal to sum I, ai dagger ai, which is just equal to sum I rho ii, which is just trace of rho, trace of the density matrix. So this is the usual type of relationship between total number of particles and trace of the density matrix. So now we have our creation and annihilation operators. But we now need to rewrite all other operators in terms of these new operators. So all other operators would be, in particular, say, the Hamiltonian. We need to be able to write the Hamiltonian in terms of these creation and annihilation operators. So the Hamiltonian is generally written in two parts. One will have what they call a single particle component. And so the single particle part of the Hamiltonian would just be, say, H0 is your usual p squared over 2m plus some single particle potential. Okay. And the way you second quantize that is like this. So H hat in this new representation is simply integral d cubed r psi dagger hat of r. It looks like you're taking the matrix element, but these are now your creation and annihilation, your field operators. Psi hat of r. Okay. That gives you the second quantized expression for your single particle Hamiltonian. Again, if we expand that out in terms of our localized orbital representation, so that's equal to integral d cubed r sum ij ai dagger aj phi I star of R H of R phi I of R. And this thing here is just the matrix element, what we've always just called H I J. That's just the matrix elements of your Hamiltonian and your localized orbital representation, right? When you including the integral of d cubed r. Those are just the matrix elements of your Hamiltonian in your usual localized orbital representation. So, finally we have that the second quantized version of our single particle Hamiltonian is just sum ij, ai dagger, aj, h, ij. And hij is just a number, right? Those are just numbers. And the operator is your ai dagger, aj. And usually, often the physicists are doing something quasi-analytically, and so it's nice to choose, instead of your localized orbitals, you choose an eigenstate basis. So you choose a basis such that h phi I is ei phi I, and then in your eigenstate basis, this starts to look very simple. Just sum over your eigenstates of your eigenenergies times Ci dagger Ci, right? Because in the eigenstate basis, the matrix elements of the Hamiltonian are diagonal. And so, you know, Ci dagger Ci just tells you whether there's an electron in state I or not. So this looks pretty simple. If there's an electron there, it's 1, not it's 0, weighted by the energy corresponding to that eigenstate, and so you get the energy of total energy of your system, right? This Ci dagger Ci is just a number operator telling you whether there's a particle in state I or not. So you're just weighting each eigenenergy by whether there's a particle there, a 1 or a 0. And then if you were to do your statistical average, this Ci dagger Ci would become a Fermi factor.
C or A is the same thing?
What's that?
C and A are the same thing?
Yeah, I switched. I'm sorry. My bad. No, well, they're not the same thing, right? Because AI is, because one is sort of your usual localized orbital representation, and the other is an eigenstate representation. Unfortunately, I used phi for both orbitals, so that's very bad notation. I just switched to Ci because these represent eigenstates. This is just my usual, say, atomic, and my usual atomic localized orbital basis. And this is in your eigenstate basis. And, you know, the most common one you see actually is the plane wave basis, sort of invariably. So, in this case, you know, the eigenenergies are Ek, your orbitals are your e to the I, k dot r, and so your Hamiltonian is just h sum k, ek, ck dagger, ck. And that takes care of your whole single particle Hamiltonian. And all the interesting stuff is in your interactions. And, you know, if we wanted to write this in terms of our scattering state basis, we could say that H, you just break it up into two parts, right? Sum k left of Ek left, Ck left dagger, Ck left, plus sum k right. So this one would be injecting from the left contact, the other would be injecting from the right contact, EK right, CK right, dagger, CK right. So these are the true scattering states of the single particle system. It's not just a plane wave, but it's like the whole wave function that evolves from injecting a plane wave from either the left or the right. And that would be your scattering state basis. And again, if we take, the thermodynamic average of this, the ones from the left become your Fermi factors from the left side. The ones from the right, CK dagger, CK from the right side would become the Fermi factors of your right contact. So the scattering states are weighted by the Fermi factors from which they originate. Two particle operators. You'll see this in every textbook. We aren't going to have time to deal with this at all. But your two particle operator is your electron-electron interaction term. Just your V of R minus R prime. Right, this is your electron-electron interaction term, and so V EE in this representation you get by doing this. D cubed R, side dagger of R, side dagger R prime, V of R minus R prime, psi of R prime, psi of R. These are all these second quantized field operators, and that's all under the integral. And now, the order is important. So psi of R prime is different from, now you have to keep track of the order, because these are all these second quantized operators that have their anti-commutation relationships. So psi R prime psi R is different from psi R prime. I guess it would just be a negative sign. You pick up a negative sign if you switch these two guys. And if you then work that all out, that's equal to sum I, J, K, L of Ci dagger, in our localized orbital representation, Cj dagger, Ck, Cl times V, I, J, K, L, where this is a matrix element defined as V, I, J, K, L is equal to integral d cubed R phi I star R phi J star of R prime V R minus R prime phi. And now these are just wave functions, so order isn't really important, but I'm writing them so you can see where they came from. Phi L of R. And these are just a bunch of wave functions at R and R prime. And it seems like I'm missing an integration. So it looks like I would need an integral over both R and R prime. Yeah. Looks like I need I need to integrate over both R and R prime because there's no more spatial dependence. Where am I going to fit that in? Integral d R prime. And I need another one over here. Integral d cubed R prime. D cubed R prime, d cubed R. This is double because I got both R and R prime. I got to integrate over everything. But we aren't going to have time to say anything about the electron-electron term. We're just going to be looking at the single particle term. Okay, so we have our Hamiltonian. We have our operators in second quantized representation. So I guess the next thing we need to do is talk about the three different representations, Schrodinger, Heisenberg, and interaction. So the first one, which you're all familiar with, is the Schrodinger representation. This is what you first learn, where IH bar ddt psi Schrodinger h psi. And so if h is not a function of time, then you go e to the minus I h t minus t0 times psi s. Okay, and the next one is the Heisenberg representation, where the wave function psi h is equal to the e to the I h t over h bar times psi s. That's your operator h up there in the exponential. And so if you do IH bar ddt of psi h, I didn't write any time dependence in the argument because there is no, you get 0. So you got two terms if you take the derivative, right? And you're going to get something that cancels. The when the IH bar ddt acts on psi s, you get, you're going to get this term, and when it acts on this, you're going to get negative of that term, and they're going to cancel.
So, I'm sorry, for psi h, my right side has t, right? I mean time dependence. So shouldn't my left side be also time dependent?
That's what I'm saying. The time derivative is 0. Right, so if we take the time derivative, I'm going to get, what am I going to get? So I'm going to get, if acting on the exponential, I'm going to get negative h times psi h. And when I act on psi, on the next part, on this, I'm going to get plus h psi h, which equals 0. Because h commutes with itself, so I can push it through that exponential term. So there's no time dependence to the wave function in the Heisenberg representation. We also need to talk about operators in each representation. So the operators, I need to look at the matrix element of an operator. So in the Schrodinger representation, these are all unitary transforms, so all matrix elements have to remain invariant. So there's a generic matrix element of an operator in the Schrodinger representation. And now I just replace the Schrodinger wave functions with the Heisenberg wave function. So that's equal to psi h e to the I h t over h bar os, which is my operator in the Schrodinger representation, e to the minus I h t over h bar psi h. So these exponentials I put in are just killing off the exponentials in the definition of psi h. This is how we define psi h. So, this exponential is just killing off this exponential, right? And then when I take the Hermitian conjugate, this one kills off, this one over here kills off the Hermitian conjugate of this. So I'm just multiplying and dividing by these exponential terms is all I'm doing. But this, since I haven't done anything and these two matrix elements are equal, this defines what I mean by an operator in the Heisenberg representation and how an operator in the Schrodinger representation transforms into an operator in the Heisenberg representation. So this is what defines my operator. OH of t is equal to e to the I ht over h bar os e to the minus I h t over h bar. Okay, so that's my operator in the Heisenberg representation. Well, as we've just seen in this representation, there's no time dependence to the wave function, right? No time dependence to the wave function, so there's got to be time dependence somewhere. The time dependence gets transformed into the time dependence of the operator. So if we take the time derivative of the operator now, So IH bar ddt OH of t. So in the Schrodinger representation, the operators are time independent. And now in this representation, the operators are time dependent. And well, so this time derivative has to act on the two exponentials. So when it acts on the first exponential, I'm going to get negative h times my Heisenberg operator back. And when it operates on the second exponential, I'm going to get positive plus positive OH. So these are all operators, and order is important. And the Hamiltonian doesn't necessarily commute with the operator, because it could be an arbitrary operator. So what we have here is a commutation relationship that defines the time dependence. So IH bar ddt OH of t is equal to the anti-commutator of an arbitrary operator in this Heisenberg representation with the Hamiltonian. And note that the Hamiltonian in this representation is the same as in the Schrodinger representation, because these exponentials commute with the Hamiltonian. So the Hamiltonian is invariant. It's the same in this representation as in the Schrodinger representation. And since these exponentials commute with the Hamiltonian, I can pull them outside of the commutator, and I have e to the I h t over h bar O s comma h e to the minus I h t over h bar. Okay, that's Schrodinger and Heisenberg representations. And there's one last one that's so the two that are used in this non-equilibrium green function theory and the second quantized representation are the Heisenberg representation, and that's what the operators are written in the Heisenberg representation to define the green functions, as we'll see. And then when we do perturbation theory, use the interaction representation. So the last one we need is the interaction representation. And here we need to break up our Hamiltonian into two parts. So there's some unperturbed part and some perturbing part, H prime, just like when we do perturbation theory, because this is really where it's used in diagrammatic perturbation theory, which is still just a fancy perturbation theory. So the definition of the wave function in this representation is that psi interaction of t is equal to e to the I h 0 t over h bar times the Schrodinger wave function. And so now if we take the time derivative of this wave function, IH bar ddt psi I of t, that's going to equal, well, acting on the exponential, I'm just going to get a negative h0 times psi I plus acting on psi s plus e to the I h0 t over h bar times this IH bar ddt acting on psi s, which just gives me h0 plus h prime psi s. Right, that's what I get from IH bar ddt acting on psi s. So there's two terms here. Let's look at them. One, 2 times over here on the right. So I have, this term acting times this, acting on psi s, and H0 commutes with itself. So I can switch the order of these two terms, right? And then I just have H0 psi I, right? That just becomes the H0 term just gives me H0 acting on psi I with a positive sign, and I have a negative sign over here, so those terms cancel. And so what I'm left with is just that other term with the H prime in it. And so that's equal to e to the I H0t over H bar H prime. And I want to keep my wave function in the interaction representation, so I'll just put in two things that cancel. So e to the minus I H0t over H bar times e to the plus I H0t over H bar times psi s, and this is just psi I. And so this, by definition, is H prime in the interaction representation. And so that's the equation of motion for the wave function. So I H bar d dt of psi I is equal to just the interaction part of the Hamiltonian in the interaction representation acting on psi I again. So the time dependence of the wave function in the interaction representation is only determined by the interacting part of the Hamiltonian. Again, we have the operators. We have to look at their time dependence. So in general, our operator in the interaction representation is equal to e to the I H0t over H bar OS O Schrodinger e to the minus I H0t over H bar. That's our general operator. And so the matrix, so IH bar ddt OIFT. Well, I'll pull down a H negative H0 acting on OI plus OI H0. That's what I get. And so that's just OI H0, the commutator H0. And again, H0 is, because this is a transformation for any operator, H0 is unaffected because this commutes with H0. So H0 is in the interaction representation, in the Schrodinger, it doesn't change. So you can view H0 as in the interaction representation because it's unaffected by this transformation. And so I could also pull out, just like we did before with the Heisenberg one, pull out these exponential terms, EIH0t over H bar OS comma H0 e to the minus I H0t over H bar. Let's define what we mean by our green functions in this representation. So we'll just write down a bunch of definitions. And these are all written in the Heisenberg representation. We'll start with sort of the fundamental thing that we're always trying to calculate. And these are, we really haven't looked at them in the time domain. We've kind of mentioned a couple times that, when there are functions of energy, it's really a Fourier transform of this t minus t prime, at least in steady state. But these are the fundamental definitions. So 1 over H bar, this thermodynamic, or in non-equilibrium thermodynamic average, A, J, dagger of t prime ai of t. Notice the indices are reversed from in the subscript for gn. And the other one, this is, you know, gn is what some people like to use, sort of if you go traditionally, it was written as g less than. Same thing, except there's just a factor of I to carry around. And this comes about because of its relationship to the other green function. So the only difference is I've got a factor of I in there in the definition of g less than. What we call g sub p, which gives you the hole density before, gp ij t minus t prime. It's 1 over h bar ai of t aj dagger of t prime. So when we write these, one way to remember this is that for the subscripts here, the second subscript always goes with the dagger. The second subscript always goes with the dagger, and same with the second, time coordinate. It always goes with the daggered variable. No matter what the order that these creation and annihilation operators come in, the order of the subscripts is always according to follows. The easiest way to say it, the second subscript and the second time variable is for the daggered creation operator. Okay, so those are the two that we're trying to calculate, and you can immediately see by the way they're defined that this is indeed, in like G sub n, the diagonal elements. If we set the 2 times equal, that is the expectation value of the finding an electron in state I, say, right? And if you think of a Fourier transform, when I set the 2 times equal, we're Fourier transforming e to the i.e. t minus t prime. I set t equal to t prime. That kills the exponential. That just means I integrate over all energy, which is exactly what we were doing to find the electron density, integrating Gn over all energy. Okay, and similarly, there's a lot of literature written. Instead of using Gp, they use a G greater than. And again, it's just a factor of I different, but now the sign is changed, so this would be a negative I over h bar times the same thing in the brackets, ditto. So again, there's a factor of I and negative I that comes into play in terms of the sort of the way these things were originally defined. And again, these come out by the relationship to the other green functions, and well, there's more to it, which we'll see how far we get. Okay, the third one, and the one we probably spent most of the time working on, was the retarded green function. I got my unit step function, my minus I over h bar times ai of t, aj dagger of t prime, plus aj dagger of t prime ai of t. And so it's just the anti-commutator of ai of t and aj dagger of t prime. And if you look at our previous two definitions, this is just equal to theta t minus t prime of, I'll just suppress the subscripts, Gn of tt prime plus Gp of tt prime and minus I. That's a minus I. Or times, what do I need? Will a minus I do it? I've got a minus I out front. Yeah, that's it. Minus I out front. Okay, and the other thing we've spent a lot of time talking about is the spectral function, which is like the total density of states within a factor of 2 pi. Oh yeah, I guess before we say that, just let me say the advanced green function, the only difference, well, okay, there's two differences. You switch the order of the t and the t prime in your unit step function, so now it's theta t prime minus t. So these things never exist simultaneously. You either have, theta t minus t prime is 1 and the other one's 0, or vice versa. If you add these two things together, we'll talk about that in a second, times the other difference is the sign on that I is switched, so instead of minus I over h bar, it's now plus I over h bar. But all the stuff that goes in here is the same. All this AI, AJ dagger, so all this stuff goes into there. So the only difference is the unit step function and the plus or minus I in that factor out front. Okay, right. And now for the spectral function. So this is 1 over h bar AI T AJ dagger T prime. It's the same stuff that went inside the retarded and advanced green functions. The same anti-commutation of these two operators. A dagger J of T prime. It's the same guys that went inside the retarded and advanced green functions. Same argument there. And so this is equal to I times GR IJ TT prime minus GA IJ TT prime. And this was exactly the relationship that we derived before in terms of, when we wrote these in terms of energy instead of time. But now you see it in terms of the operators, in terms of the definition, in terms of the operators. And it's also equal to, I'm running out of room, but I'd like to write it all together, Gn IJ TT prime plus GP IJ TT prime. So these are all the relationships we derived earlier, and now you see they also hold true in terms of their definitions, in terms of the creation and annihilation operators.
What is the physical significance of T and T prime here?
Same as the physical significance of I and J. So I inject the particle in state J at time T prime, and I see the response in state I at time T. And I mean, that's the way you interpret the retarded green function, because that is an impulse response. So the correlation functions are, again, correlation functions, which is sort of harder to interpret what we mean by the off-diagonal elements of the correlation. It's like the off-diagonal elements of the density matrix, right?
So is it like one particle is being created at point J at T prime, and for that we are calculating the response at time T at point I?
Like you put it in the system and state J at T prime, take it out in state I at time t.
So are these I and J's are like state or just position here?
Well, if you look, these are the creation and annihilation operators for our localized orbital representation. That's the way I'm writing them. Like the same basis, our tight binding basis we've always been using. You can write these all in terms of using replace all the A's with your field operators, your psi and psi dagger, and then you have the same, your retarded green function and everything in terms of your position representation, R and R prime. So instead of I and J, you'll have R and R prime and T prime. And that's just your green functions in the position representation. If you write all these definitions using your field operators instead of these AI and AJ, you would have, psi of RT, psi dagger, R prime, T prime. And that's your green functions in the position representation.
And the Green's function we are discussing here, are those like specifically written here, are these single particle or are you considering multi-particle? Can
Well,
you call it
when you just have, I guess when you just have two operators, they call it single particle green function. You need four operators. Just like, when we quantized our Hamiltonian, when we quantized a single particle Hamiltonian, we end up with two operators as a product. When we quantized our two particle Hamiltonian, we ended up with four operators, product of four operators. So I think as long as it's just what they call quadratic, it's a single particle Hamiltonian. Right? This is quadratic in the operators. We've been working in terms of energy all this time and never meant, so the relationship between the green functions and correlation functions we've been using and these just going from time to energy. So we've been just not worrying about subscripts, just going back and forth between time and energy. Everything we've been doing has been steady state. We haven't worried about time dependence either. And so in steady state, this is the relationship between the time and the energy. So that's true for all of the green functions and correlation functions. It's just a Fourier transform of the t minus t prime time difference coordinate in steady state. So this is true in steady state. So the assumption in steady state is that any time dependence is only a function of the time difference, t minus t prime, since nothing is varying as time progresses. So the only time dependence is in the t minus t prime coordinate. If you then were to apply, an AC signal or a step voltage, then you would have something varying as a function of sort of the center of mass, what they would call the center of mass time coordinate, your t plus t prime over 2 coordinate. Right? Your whole system is changing as a function as time progresses. This is steady state, and now let's go back and look at that spectral function. So there's our spectral function. And now so here's one question. What is ddt, the time derivative, dt a of t comma t? What is that going to be? So I'm setting t equal to t prime and asking what's the time derivative of that.
Conversion with the Hamiltonian?
You're thinking kind of along the right direction, but you got to keep thinking a little more. Forget the Hamiltonian. You don't even need to worry about a Hamiltonian. Set t equal to t prime. And what have you got? How about now? What's that thing in the curly brackets? What are the?
Anti-commutation.
It's an anti-commutation. What's its value? You can evaluate that.
Delta ij.
It's got to be either, yeah, it's
It is
delta,
zero delta.
delta ij. So what's ddt of delta ij?
Step function.
It's 0. There's no time dependence to a Kronecker delta function. Right?
Yeah.
It's just delta ij. It's either 1 or 0. Not a function of time. This is, you know, the what do you call it? When you set the equal time commutation relation. I once asked this on a prelim. I thought it would be an easy question for everybody. It's pages and pages of commutation with Hamiltonians. Oh my God. That would be a freebie. A one-liner. Okay, it's 0. Okay, 0 is ddt of a Kronecker delta function, which is 0. But this brings us back to a homework problem you had, like, I don't know, maybe in homework 1. So, I think you were asked to show that the integral of the spectral function was equal to 1. The integral of the diagonal, something like integral dE over 2 pi aii of e was equal to 1. I think you had to show that the hard way by doing some integration in one of your homework problems. If I look at the definition of what I mean by a of e, it's just related to a of tt prime like that. It's like integrate dE over 2 pi integral dt minus t prime e to the I e t minus t prime over h bar a of t minus t prime. I guess I'm going to get just delta, right? They're just going to give me a delta t minus t prime, which will kill off, this integral and that exponential. This gives me a delta t minus t prime, which collapses the integral over t minus t prime, and I just get a of t equals t prime, right? And a of t equal t prime is just 1 over h bar. You just show that, if I equals j, we're looking at this now, this is just 1. So a of t equals t prime is just 1 over h bar. Oh, and actually this gives me like h bar, right? I got an h bar here, I forgot. So this gives me like h bar delta t minus. So that 1 over h bar kills the h bar, and I got 1, which is what you were asked to show in like homework 1. So this shows that, very generally that, once you see the definition in terms of the operators, it's clear that when t equals t prime, then a is just going to give you 1, because it's just an anti-commutation relationship. Okay, so I guess it's time for a break, and I need to get my power supply since I forgot to bring it down here. So let's take a break.